Hello class, today we're going to start chapter 13 of the 4040 class. This chapter is about simple linear regression. So the objectives of this chapters are for you to learn how to use regression analysis to predict the value of a variable based on the value of another variable. So the variable we're trying to predict is called the dependent variable. The variable using to predict the dependent variable is called the independent variable. And of course, the other objective is for you to understand the meaning of the regression and the regression coefficients, the intercept and the slope. So the first thing is for you to understand the intuition behind linear regression. And for that, let us first go back to correlation. So we saw in previous chapters that when two variables move together, we call them correlated. What do we mean by move together? We mean that when one of them is higher than its average, the other one tends to also be higher than its average. It can also be inverse correlation when one variable is above its mean, the other one is below its mean. So they are inversely correlated. Now we saw that to check whether variables are correlated or not, we use something called the correlation coefficient. That coefficient measures the strength of the association between the two variables. However, there are a few weaknesses to this, because the correlation is only concerned with the strength of the relationship, the correlation or the inverse correlation. The two variables are treated equally, and you cannot use one to make predictions about the other. For instance, you could say something like high temperatures are correlated with high sales of ice cream, but you wouldn't be able to say anything more than that. That's where regression comes in. Regression allows you to go beyond that simple statement of correlation. You can start making predictions. So in regression, we don't treat the two variables equally. We call one of them dependent and the other one independent. You can also call them explained and explanatory. And in this framework, you can quantify the relationship and you can use it to predict the values. For instance, taking the same example as previously, how much more ice cream can I sell if it becomes 1 degree hotter? So I've already said that today we're talking about linear regression. What do we call linear regression? Well, relationships between variables can have different shapes. On a scatter plot, you can see how variables relate to each other. When the scatter plot of a variable against another variable tends to form something that looks like a line, we call that a linear relationship. That line can be sloping upward or it can be sloping downwards. However, we need that to be a straight line, like in geometry. If it's a curved line, we do not call that a linear relationship. We call that a curvilinear relationship, but we're not going to talk about those in this class. On the scatter plot, you can also see the strength of the relationship. So what do we call a strong linear relationship versus a weak linear relationship? Be careful, it doesn't have to do with the slope. It's about the spread of values along this general linear tendency. So here we see that the values are pretty close to this general linear tendency. Here the same thing, they are pretty close. They're a little bit away, but they're not far. We call that a rather strong relationship. If we have a lot of spread like this, we would call that a rather weak relationship. Now, when do you have no relationship whatsoever? That has to do with the slope. There's only one slope that is no relationship, and that is the flat line, the zero slope. And note that it doesn't matter how spread or concentrated the values are around it. In either case, because the line is horizontal, we say there is no relationship. In other words, it doesn't matter what the value of x might be, that has no effect on what the value of y might be. So I've been talking about these relationships that we can see visually on the plot. Well, how does that relate to regression lines? Well, these lines that we were drawing, those are regression lines. The point of regression analysis is to fit these lines through the data. And the point of it is to try and fit these lines as well as possible. Again, in this class, we only look at the linear regressions. The curved ones exist. We're not going to talk about them though. So what is the point of regression analysis? Well, we use regression analysis essentially in two ways. One is that we're going to use it to predict the value of the dependent variable based on the value of the independent variable, and sometimes many independent variables. The second thing we tend to use regression for is to explain the impacts of changes in the independent variable on the dependent variable. So taking that ice cream example again, how does a change in the outside temperature impact my prospects for selling? So these are two key terms that you need to really be familiar with: the dependent variable and the independent variable. Dependent variable is the one we wish to predict or explain. Therefore, as I said, we also call it the explained variable. And the independent variable is the one that we use to predict or explain the dependent variable, also called explanatory. Now, be careful, an important caveat: these relationships are not necessarily causal. Sometimes you may want to interpret them as causal, like in our ice cream example, where it seems to be very clearly a causal relationship, but that is not the general case for regression. What you are finding is associations between the variables. You can use these associations to make predictions or explanations. That does not mean that you necessarily revealed a causal relationship. So how does regression help with prediction? Well, when you have your plot of data here and you fit a line through your data, you can use that line to make a guess about what the value of y might be for any value of x. So here, for instance, you only have 13 values of x for which you know y. You would like to know y for this value, which doesn't actually have an observation. Well, what's your best guess? Your best guess is that it's going to be pretty close to this line. So in this sense, you are using the regression line to predict what y might be given the value of your x. And that's how you get a pretty good guess for y. So now that you get the intuition of this, let us go into the simple linear regression model. So why do we call it simple? Simple just means one independent variable, one explanatory variable. That's one x, and we're going to call it x. In the next chapter, you'll have x1, x2, x3, etc. For now, don't worry about it, there's just one x. The variable we wish to explain, we're going to call it y. And we assume that the levels of y are somehow related to the levels of x. And we think that relationship between x and y could be described by a linear function. Meaning what? Meaning that you can write it as y is equal to a times x plus b, right? That is a linear function. And that linear function defines a linear relationship between y and x. Now, by convention, economists don't like to use y equals ax plus b to describe linear regressions. Rather, instead of b, we use beta 0, and instead of a, we use beta 1. So we say y equals beta 0 plus beta 1 times x. Now, notice that is the same equation. We just change the name of these constants that define the equation. We change the names of the parameters of the equation. Why do we do it that way? Well, because later we're going to be adding more equations, and so these notations make more sense when you have more terms. So get used to this. We call them y equals beta 0 plus beta 1 x. So visually, what does our model look like? Well, we have the x variable on the x-axis, the y variable on the y-axis. And we have 5 observations of a variable x and a variable y associated with each other. So we can plot the 5 points. The question of linear regression is, what is the best line that we can use to represent the relationship between x and y? Now in this case, it's obvious. We can just draw this line through all of the points. Now this line can be defined by an equation, and the equation would have, of course, an intercept and a slope, and we call the intercept beta 0, it's right here graphically, and we call the slope beta 1. So y equals beta 0 plus beta 1x is the equation of the line that fits through our data. And for every xj in our data, we can find the associated yj in the data, because yj is equal to beta 0 plus beta 1 xj. In this case, everything is lining up perfectly. Now, if you have an xi that is not in your data, you can also make a pretty good guess about what the y would be. You would say its yi is equal to beta 0 plus beta 1 xi. Because if the formula works for the other y's, it should work pretty well for this one. Okay, but what would we do if the points didn't actually line up perfectly to begin with? Well, again, we want to ask the question of what is the best line that we can fit through this data. And it would look something like this. It would have an intercept and a slope. It would have the same equation. And we would use the same procedure to predict the value of y given x, even if, to begin with, our y values were not perfectly aligned on this slope. If we can say that this slope is the one that best fits through the data, this is still going to be our best guess for yi given xi. But you may have noticed, what's this point doing here? That is the value for y given xi. It's not here, it's there. We actually know it. So the predicted value is not accurate. It is different from the actual value. And what do we call that difference? We're going to call that difference between the predicted value and the actual value, we're going to call that epsilon, epsilon I. We call it the random error. This is the random error associated with this particular x value. And for every value xi, we can write the corresponding yi as beta 0 plus beta 1 xi, which is the prediction, plus error, which is drawn here. So with our regression line fitted through these dots, we have an error here for x1, we have an error here for x2, another one for x3, another one for x4, another one for x5, and like this for our whole data. And that is what we call the simple linear regression model. The simple linear regression model is the equation that links the dependent variable yi to the independent variable xi with a linear equation, that is the linear component of the model, and an error, which is the random error component of the model. You need to be familiar with all these terms: the dependent variable, population intercept, population slope coefficient, independent variable, and random error term. Now you notice that I called them population intercept and population slope coefficient. Why is that? Because we assume that these betas are the actual true values that exist in the population. We don't actually know them, but we assume that they exist. And what are we going to do? Well, we're going to estimate those values based on a sample. So the previous equation was our regression model. Now, the equation on this slide is our prediction line. That equation provides an estimate for the population regression line. And you notice we'll give them all different names to show that these are predicted values rather than population values. So y with a hat is going to be the predicted y, the estimated y. And then we're going to use B0 for the estimate of the regression intercept, B1 for the estimate of the slope, and xi for the actual value of the observations. Note that xi is the only one that stayed the same from the previous model to this regression equation. Now the goal of regression is going to be find the best fitting line. In other words, to find the best estimate of this linear model that we think is the true model. And how are we going to find this line that fits the best? Well, we're going to use your good old friends, the sums of squared errors. You've already seen the sum of squared errors when we talked about ANOVA. So here we're going to use the sum of squared errors again, this time to find the least squared regression line. How does that work? Well, we try to find the line that gives us the smallest sum of squared errors. Remember, what are the errors? The errors are the distances between this line that you fit and the actual value of y. Here's error 1, here's error 2, here's error 3, 4, 5, and 6. Now, it doesn't matter to us whether the actual value is below the line or above the line. That is why we square it, so that the negative signs turn into a positive. And so if you square all of these values and you take the sum of it, what you get is an idea of how far these points are located from this line that you drew through them. And so by choosing the line that minimizes the sum of squares, we find the line that fits the best through this data. You can kind of see that visually. If you were to draw a line right here, is that our best fit? Well, clearly you can see that it doesn't really fit through the data. What is the sum of squares? This E1 is very big, E2, E3, E5, E6. All of these seem to be bigger than the ones we had before. So the sum of squares is obviously going to be really big. So this is clearly not the best fit, and it also clearly doesn't have a small sum of squared errors. This one, it seems, is pretty good at minimizing the distance between epsilon 2, epsilon 4, epsilon 5, and the line. However, look at what happens to the other values. They are very large, and so when you square those and add them to the sum, you're finding that this sum of square is going to be very large as well. So this is clearly not the best fit either, and it is clearly not the smallest sum of squared errors. Now going back to the line that, if we eyeball it, looks the best, indeed epsilon 1 is small, epsilon 4, epsilon 6 are pretty small, epsilon 2, 3, 5 are a little bit larger, but nowhere close to as big as what we had with the other lines. So this is the one we're going to retain to make our predictions. And hopefully you've seen visually why minimizing the sum of squared errors is a good method to find a line that fits well through your data. And now the question is going to be how to find an equation for this line. Well, to find this equation, we need to find b0 and b1, and those are found by minimizing the sum of square differences between y and hat, between the actual y and the predicted y, where the predicted y hat is beta 0 plus beta 1 xi. The calculations to actually find them I'm not going to show you here, but they are available on Pearson if you go online and look for them. But for us, we are in luck. We are just going to use the methods that Excel has that computes those coefficients for you. Now, hopefully by this point, you've developed an intuition for what the regression line is. Now let's talk just a little bit more about what the interpretation of the slope and the intercept of this line are. The intercept, b0, is the estimated mean value of y when the value of x is 0. This makes perfect sense because if x is equal to 0, the equation just becomes 0 alone. So that is the estimated value y when x is 0. Now b1, on the other hand, is the slope of the line. How do we interpret the slope of the line? Well, that is the estimated change in the mean value of y that results from a 1 unit increase in x. Again, this should make sense to you because that is the definition of the slope. X increases by 1 unit, then y increases by how much? By the slope. So your intercept is the estimated mean value of at 0, and your slope is the estimated change in the mean value of y, or a 1 unit change in x. Okay, so let's go over a little practical example here. So just imagine you have this problem. You have a real estate agent that wishes to examine the relationship between the selling price of a home and the size of that home. The agent takes a random sample of 10 houses, and the dependent variable, the one that you wish to explain, is y, the price of the house, in this case expressed in thousands of dollars, and the dependent variable, the one you're using to try to explain your y, is x equals the square footage. So let's imagine this is the data you obtained. We have the price of different houses in thousands of dollars and the square footage of these houses, square feet. You can plot this, the square footage on the x-axis, the house price on the y-axis. As you see, you get a scatter plot of points. They are not perfectly lined up. The square footage doesn't perfectly predict the price Here, for example, you have houses that are a little smaller than these, but a little more expensive. However, in general, you can see that there is a tendency for larger homes to be more expensive. So if you ran a linear regression on this sample, you would get this output. This is the output from Excel. Where do you find your regression line? It's right here. It gives you an intercept and a slope on square footage. So this first coefficient is b0, it's the intercept, and the second coefficient here is b1, that is the slope. We can plug these into our regression equation. We get that the house price can be estimated with the equation 98.24, that's the intercept, plus 0.1097 times the square footage. This is our linear regression that estimates the price of a house given its square footage. So if we go back to our scatter plot, what does our prediction line look like? Well, it is this line, this red dotted line here, that here changes into a black line and back to the red dotted line. Why is the line red and dotted on the sides? Because out here, we're going to say that the line doesn't make much sense. It makes most sense between these values here and there. Whereas the intercept, however, it is way down here. The intercept is the value of this line if you were to extend it all the way down to 0. So let us focus on interpreting b1, the slope. So b1 is this 0.10977. You multiply the square footage by b1. So b1, we saw the definition, estimates the change in the mean value of y as a result of a 1-unit increase in x. Putting this in our context, b1, 0.10977, tells us what the mean value of a house increases by for every additional square foot. So for each additional square footage of a house, you get 0.19 thousand, meaning $109 added to the price of the house. Now you might ask, what is the interpretation of B0 then? Well, in this case, it doesn't really make sense. 9824 is the intercept of our regression line. It is the estimated mean by when the value of x is 0. But in this case, a house cannot have a square footage of 0, then there's a house. In this particular case, B0 has much less of a practical application than B1. How would you use this for prediction? Well, let us do an example. If you wanted to predict the price of a house with 2,000 square feet, all you would have to do is plug in this square footage into our regression. So the estimated price of a house is 9825 plus this times the square foot. Plug in 2,000 and you get 317. Remember, this is in thousands of dollars. So a 2,000 square foot house is estimated to $317. That is the predicted price of the house given our prediction line. Now be careful, as I said earlier, using predictions like that is really only valid within a certain range, which is the range for which you had values. We don't want to do that out here where we have the red dotted line or down here. This is the range that we call the relevant range for interpolation, and out here we would call that extrapolating. Well, the idea is do not extrapolate beyond the range of the x that you observe. Right here you observe x's between around 1000 and 2500. So this is the range in which you may interpolate. Here to avoid extrapolate. Why do we want to do that? Well, because nothing tells us that this data remains so nicely well aligned outside of the range we have. It could very well be that the data has a shape like this that looks linear around where we saw it, but is not linear outside of these bounds. Or it could be something like this. So when you do this, you run the risk of making big mistakes. The next thing we see is how to look at how good a regression line is. Well, we're going to do that by splitting the variation once more in a way similar to what you did already in the past chapter about ANOVA. Here we're going to split the total variation into two parts. The total sum of squares are split into the regression sum of squares and the error sum of squares. The total sum of squares you're familiar with. It's a difference between the y's and their mean. squared. Regression sum of squared is the distance between the predicted y's and the mean of the y squared. And the error sum of squared is the difference between the actual y's and the predicted y's squared. You already know this. This is what you minimize to get your regression line. So the total sum of squares is a measure of the total variation, and it measures the variation the yi values around their mean y bar. Regression sum of squares, we also call the explained variation, is a variation that's attributable to the relationship between x and y. And the error sum of squares, the SSE, which we also call the unexplained variation, is the variation that's attributable to factors other than x. You know them, that's why you call it unexplained. And by the way, when you think about it in this sense, it helps you understand why minimizing SSE is a good way to find the regression line. What you're doing is you're trying to minimize the amount of unexplained variation that in your visually, what does this look like? Have this line here that is your y bar. You have this line here that is your y hat, the predictions. The total variation is the distance between your yi and the mean. The regression variation, as you see, is the distance between predicted y and the mean. It is the distance from mean that is explained by the regression. And this is the part that is unexplained. This is the error. Now Excel is going to give you these measures of variation in a table that looks like this. That should be familiar because we just talked about ANOVA. And it gives you the SST, which is equal to the regression sums of squares plus the residual sums of squares. Excel calls it residual, we call it error. That is the same concept. So now to go back to our original question, which was how good is my regression? Well, we're going to compute something we call the coefficient of determination called r squared. This coefficient of determination, we're going to express it as the regression sum of squares divided by the total sum of squares. Now you should be getting the intuition already what this means. Regression sum of squares is the variation that is explained by the regression. Total sum of squares is the total variation. So what is the coefficient of determination? It is the portion of the total variation, the dependent variable, that is explained by the variation in the independent variable. This makes sense as a measure of quality. It tells us precisely how much were we able to explain with our explanatory variable. Now note that because SST is SSR plus SSE, R squared is always going to be somewhere 0 and 1. And the closer you are to 1, the better your regression. Why? Because if R squared is close to 1, it means that almost all of the total variation in your y is explained by variation in your x. So when R squared is high, we say that x explains a lot of the variation in y, so that's a pretty good regression. And when R2 is low, close to 0, we say that x does not explain much y, and so the regression is not. So here are a couple of examples. In both of these cases, the r squared would be equal to 1. Dots line up perfectly with the regression line. R squared is equal to 1. Here also, r squared is equal to 1. Here you have examples that are slightly weaker. In this one, again, there is no slope at all. There is no linear relationship between x and y. This is when r squared is equal to 0. And it is equal to 0 independently of how well these values fit on the line. So where do you see your coefficient of determination? Well, you could read it out of your ANOVA output right here. However, it is also given to you right there. So you don't necessarily need to go back and compute it because it is given to you by Excel. Again, how would you interpret that specifically with a value of 0.58082? You would say that 58.08% of the variation in house prices is explained by variation in square feet. So that was the first concept of quality of your regression. The second concept that is important in this case is the standard error of the estimate. What is the standard error of the estimate? Well, it is the standard deviation of the variation in observations around the regression line. So the standard error of the estimate, we call it SYX, and it's a measure of how good your estimate is in your regression. Now, this equation may look a little bit unfriendly, but it's simply the square root of your sum of squared errors divided by n minus 2. Again, Excel gives it to you right here in the output, but you can check that it could also be computed right here from the sum of squares and the degree of freedom. Graphically, what does SYX measure? Well, it's a measure of the variation of your observed value around the regression line. So if your observed values are bunched around the regression line, that is a small SYX, and if they are spread apart from the regression line, that is a large SYX. Now, importantly, the magnitude of SYX should always be judged relative to the size of the Y values. In other words, the standard errors don't have an absolute value like the R squared between 0 and 1. Rather, it depends on the units and it depends on the values you have in your data. So for instance, here we have an SYX of 41.3 that is relatively small relative to the housing prices we have because they're in the 200 to 400 range. Okay, let's move on. A few quick words on the assumptions of the linear regression model. Well, there's an easy mnemonic for them. It's line, L-I-N-E. The L stands for linearity. We assume that the relationship between x and y is linear. I stands for independence of the errors, meaning that we assume that the error values are statistically independent. That's a bit of an obscure concept. Let's not get into it right now. N stands for normality of the errors, which is the assumption that the errors are normally distributed. Again, a little bit obscure for right now. And the E stands for equal variance, which is also called homoscedasticity. This again is an assumption on the errors, and what it says is that the probability distribution of these errors has a constant variance. Now again, those are slightly obscure concepts and we're not going to get into them right now, but it's important to talk about them just so that you remember and are aware that regression is not always valid. There are assumptions and there are sometimes strong assumptions. So you should be aware of that fact that you cannot simply blindly trust anything that comes out of the regression. There are ways to test whether these assumptions are valid or not, but that's for subsequent chapters. And this brings us to the last part of today's lecture, which is about using regression for hypothesis testing, or in other words, what we call inference. So the exact same way we used to have standard errors around the mean at the beginning of the course, we are now going to have standard errors around the coefficients. In this case, we're going to have a standard error around B1 and also around B0, but that's less interesting. We're going to focus on B1. And because we have standard errors around B1, well, that means we can run tests, statistical tests, for the value of B1, the same way we used to run statistical tests for a mean or a proportion or a variance. So in this case, the standard error for the regression slope coefficient B1 is estimated by this equation. So this is the SYX that we determined earlier, and this is the square root of the sum of square deviations from mean in the x variable, not the y variable. Don't worry, you don't need to know this by heart for the test. So to make inferences about the slope, we're going to use a t-test. So we're going to do a t-test for a population slope. You're going to recognize all of this because it's going to be very similar to a t-test for population mean, except in that case, we're testing the slope. So we're not asking a question about population mean, we're asking a question about this linear relationship that might exist between x and y. And again, you're going to recognize this. We're going to have a null and alternative hypothesis. H0, the null is going to be that beta 1 is equal to 0. There is no linear relationship between x and y. And H1 is that beta 1 is different from 0. There is some relationship between x and y. It may be positive or negative, but at least it is not 0. That is our H1. And of course, the beta is the population parameter, and we estimate it with the b. So our test statistic is going to look exactly the same as our test statistics before. It is the value of the estimate minus the value that is hypothesized divided by a standard error. So in this case, b1 minus beta 1 divided by SB1. And this t-stat has degrees of freedom equal to n minus 2. All of these should look very familiar. It is similar to all of the hypotheses tests that you have been using so far. So let us go back to our example with the housing prices. We estimated this regression equation. The slope in the model was 0.1098. Now, the question is there a relationship between the square footage of the house and its sales price? Well, you might say, we know there's a relationship. There's this number here. However, the question now has become, is this relationship statistically significant? Is this number statistically significantly different from zero? We can compute our t-stat using the formula that I just showed you, or we can just read it straight out of Excel. Here it is. And as always, how are we going to test for it? Well, we're going to compare that t-statistic to some critical t. In this case, our t half of alpha was at 2.3. 3.3 is high above that. It's in the rejection region. We reject H0. Beta 1 is not equal to 0. There is a relationship. So in this case, we can say there is sufficient evidence to say that square footage does affect the house price. So in this case, there is sufficient evidence to say that the square footage affects the house price, or at least is statistically significantly related to the house price. Of course, we can again do that same test with the p-value. The p-value is given to you in the last column here after the t-stat. And as always, if the p-value is low, H0 must go. And so we reject H0 because the p-value is less than alpha. You might ask whether you can do this with the confidence intervals. Yes, indeed, you also have confidence intervals around the estimate of the slope. You can calculate it using this equation, again with the degrees of freedom on the t being n minus 2, or you can just read it from this last part of the table. Excel here is giving you the 95% confidence interval. And of course, we interpret this exactly the same way as we used to do it. So the lower bound is 0.03, the upper bound is 0.18. This confidence interval does not include 0, so we are 95% confident that this number is different from 0. So before we end, let me say a few words on the pitfalls of regression analysis. The biggest pitfall is not realizing that there are assumptions in a least square regression and trusting the least square regression without thinking about the assumptions that underpin it. Now, of course, I did not tell you much about those assumptions, and you haven't yet learned how to test them, but you should already have the reflex of thinking that the regression is not necessarily something you should blindly trust. And there are also a few things you can do to avoid the pitfalls. So, for instance, you should never use a regression model without a minimal knowledge of the subject matter. You definitely know enough to not extrapolate outside of the relevant range of data that you have. And finally, you can avoid the cause and effect pitfall. Do not interpret the relationships that you find in your regressions as being causal relationships. They are not necessarily so. And finally, the single most important strategy for avoiding the pitfalls of regression is to start by running a scatter plot of x versus y and look at whether a possible relationship might exist. Don't just run the numbers, look at the data first. This is the first, second, and third most important rule of regression. Always plot your data first. And here is an example of why you might want to do that. These four plots of data have the exact same regression results, but as you see, they are completely different. So as a summary, what did we do today? First of all, we talked about how to use regression analysis to predict the value of a dependent variable based on the value of an independent variable. We talked about how to understand the meaning of the regression coefficients b0 and b1, and we talked about how to make inferences about the slope b1. That is all for today. Thank you for listening. I hope it was helpful.